Hello and welcome. This recording is session 3 of an 8-part series on the topic Moving Towards Improved Earthquake Performance and Resilience for New Buildings. My name is John Sherstabatov. I'm a structural engineer focusing on earthquake engineering. This series of recordings is part of the MBAR initiative by BC Housing. It includes and promotes the consideration of resilience for new buildings for natural disasters such as earthquakes. The list of 8 sessions is noted on this slide for your future reference. This session is titled Seismic Isolation for New Buildings. So what are seismically isolated buildings? There are isolation bearings beneath the foundation and the structure as illustrated on the right. The lateral shaking is significantly reduced by decoupling the structure from the ground. The deformation occurs at the isolators to dissipate the earthquake energy, rather than dissipating the earthquake energy by ductility or damage in the structure. The contents in the structure are thus better protected. And you can hear the term called base isolation, where the isolators are installed at the lowest level beneath the structure at the foundation level. So from a structural engineering point of view, we use something called a design response spectrum. You can see the base shear on the y-axis, the period on the x-axis. And as you increase the period of a building, the earthquake demand, the base shear goes down. So what base isolation does is it shifts the period far to the right. And as you can see, the base shear reduces significantly. And also seismic isolation increases the damping, which further reduces the base shear. So there's a significant reduction and the building can continue to perform in an elastic manner. So graphically, per the cartoons presented in previous sessions, the seismically isolated building for the full code level earthquake will have that, no structural damage performance noted by the blue arrow. There are quite a number of different types of isolation bearings, elastomeric bearings, and I'll just focus on the illustration on the right, a lead rubber bearing consisting of a laminate of steel and rubber plates with a lead core. As the isolation bearing deforms, the lead core dissipates the energy. The rubber brings it back to its original condition, and the steel plates make sure it's stiff enough to support the vertical load of a building. There's also sliding bearings, both flat and spherical. The one on the right, you can see it's called a friction pendulum, where the top piece slides inside a dish, so it goes up and down inside the dish. The earthquake energy is dissipated by friction, and then it comes back to the bottom of the bowl after the earthquake. And for both or all isolation bearings, they can go through earthquake after earthquake without needing repair. There are provisions for seismic isolation in all the current codes we use here. It does require 3D nonlinear dynamic analysis. 2 suites of 11 ground motions need to be modeled. The period of the isolated structure needs to be moved far enough to the right, increased, so it's at least 3 times the period of the fixed base structure. This ensures the structure above the isolators moves almost as a rigid body. The modeling accounts for all expected variations in material properties of the isolators over the design life of the structure. Prototype testing is required for 2 full-size specimens to make sure that what is modeled is reflective of the actual devices. And then every isolator that is produced and sent to the site usually is tested, but the code right now only requires a representative samples. But most projects just test every production isolator before it's shipped to the site for tremendous quality control of the performance. So the isolation plane can be above grade, like the figure on the left, where no moat is required, or it can be below grade, the figure on the right, where a moat is required to make sure as the building moves side to side, it doesn't, of course, impact with the ground. An aspect ratio of 6 to 1 or so of a building of height to width will make sure there's no uplift at the isolators. But again, larger aspects ratios can be possible. Just for clarification, the seismic isolation system reduces the horizontal components of shaking, but the vertical shaking component is still there, similar to a fixed base building. but that is typically not the damaging component of ground shaking. So what are some general other provisions? They need a minimum stiffness for wind load. Of course, you don't want the building moving under design wind load. All the components above the isolation plane are to remain elastic or undamaged. And again, for a mean plus a standard deviation of all these analyses that are done, and a modest level of detailing for ductility. The isolators, of course, similarly must accommodate the prescribed movement from all the analyses, the nonlinear analyses done. And again, to be on the conservative side, a mean plus a standard deviation of the movements of the isolators. So tremendous reserve capacity of the isolators for the predicted ground movements. Some general considerations. The floor diaphragm above the isolators, above those red dots in the figures, needs to be very stiff to be able to distribute the lateral loads nearly equally to all the isolators. The structural system above the isolation plane, it's preferable to have a well-distributed seismic force resisting system, not a core tower as you see in many buildings, but a well-distributed system, again, to minimize uplift at the top of that diaphragm. And a key aspect, all mechanical, electrical, and architectural elements crossing the isolation plane need to be designed to remain functional while accommodating the horizontal movements. In BC, it's in the range of 200 to 500 millimeters, depending on where you are in BC. So these buildings have been proven from their performance in previous earthquakes. Here's an example of a building in Kobe, Japan. The building on the left, which shows the isolated building. You can see at the base, the ground was shaking at a 0.4 G level. The building itself saw de-amplified accelerations of 0.12 G and uniform across the entire height of the building. On the right, a nearby similar fixed base building saw 0.37 G at the base, and you can see the tremendous amplification and shaking towards the top of the building. And you can see the roof of the two structures, about a difference of a factor of 10 in the shaking. So tremendous benefit to the contents in a base isolated building. And here's a brief video of the shaking that can happen at the base of a fixed base building compared to what I'll show you in a base isolated building. This will be contrasted to a hospital that was base isolated in Japan that was subject to a magnitude 9 earthquake. And this video illustrates the significantly reduced level of shaking. There's still a little bit of shaking, of course. See, there's no panic or alarm with the occupants. And again, at the end of the video, there's even a gentleman casually looking out the window to see what is happening around the building. So significantly reduced compared to a fixed base building. This video illustrates what's happening below the building. This is the isolator. The isolator is deforming to dissipate the earthquake's energy, all the while supporting the vertical load of the building. And ultimately, it will move back and forth to accommodate the ground movement and come back to its original position, able to accommodate earthquake after earthquake. So base isolation projects have been done in at least 15 countries for over 30 years now. So it's proven and it's being done. This just illustrates a few examples of the types of buildings that are being isolated. These are a couple of hospitals in the US and in Japan. Emergency centers are common buildings to be isolated, some facilities in the US and Japan. A few examples of housing and a museum in Japan that are base isolated. Just an example of a building in San Francisco, the De Young Museum. Again, the isolators in here are below in the basement level. designed for a movement of 660 millimeters. And again, that movement is hidden because it's covered, it's in the moat. And again, this was selected to be isolated to provide protection to the museum's collections. The figure on the left shows that elastomeric bearing in the basement. In the middle, a sliding bearing. These are commonly used in combination. Again, and in the basement, this is the moat, the gap between the building on the right and the earth on the left, and the moat cover up above. And this allows movement with the building not getting into contact with the ground. Some other examples in other buildings where moat covers fit in quite nicely with the sidewalks. And the one on the right, for example, it's a flip-up lid, whereas the building moves to the left relative to the sidewalk, the lid will flip up and move, and it'll move back, and it's supported, so obviously it doesn't fall into the opening, and it comes back to this position after the earthquake. Just a few examples of mechanical and electrical services. It's a very sophisticated science now to get articulated joints to make sure mechanical pipes can move as the building moves without losing functionality, and electrical cables and the like. So in summary, there are design provisions in our current codes. It's a very proven technology and used in many countries today. It can provide no structural damage performance for the full code level earthquake. It significantly reduces shaking to the non-structural components within a building. But in our current codes, it does require 3D nonlinear analyses, and it does require, detailed attention to moat covers, the architectural, mechanical, and electrical services that cross the isolation plane. So again, if you have a building that you really want to protect the contents and have an undamaged structure, consider seismic isolation. If you would like more information on this topic, please contact me at the email address noted below. For more information on MBAR, there's an email and web page address noted. Thank you for attending this session, and I hope you join me again for more sessions in this series.